Does it record? Hope so. Yeah, it looks good. Welcome everybody, and in particular welcome Andreas. Thanks for giving us a talk about something Haskell related, but not Haskell itself, Isabelle HOL, an interactive theorem prover. But probably that's best explained by Andreas himself, who's an expert in that domain.
Right,
Thanks.
Thanks for the opportunity being here and being able to tell you a bit about Isabelle HOL, and I'm trying to make this as interactive as possible. So if you have any questions, just interrupt me, and I'll try to do my best to answer the questions. I've been using Isabelle for the past 10 years, pretty intensively in my work. I'm a postdoc at the moment here at ETH. I'm doing various proofs and formalizations in Isabelle, and today I thought I'll start with something very, very basic. Let's do it interactively. The overview, well, I'll first briefly tell you what Isabelle is, then let's look a bit of how you do functional programming there. But programming is really the small part that you spend your time on. Most of the time you spend with Isabelle is actually writing proofs about your programs, proving properties, and I thought I'd go for equational reasoning in today's presentation, maybe talk a bit about termination proofs, reasoning about infinite data. It depends how far we get. So, as I said, please interrupt me if there's anything. If you have any questions, let's make this as interactive as possible. So, what is Isabelle? Well, it's a proof assistant. What does that mean? Well, it's a system where you can write, let's say programs, but you can write definitions of mathematical concepts in a mathematical language that can be parsed by the system, and you can also write proofs by the proofs basically in mathematical style. We will see that in a moment. Proofs of properties. Properties need to be expressed also in some way, and there's just the rich theory of mathematical logic that you can use. So you can use the usual quantifiers that you have, like you can write conjunction, disjunction, you have implication, negation, and I hope you've all seen them sometime in your life. You have quantifiers, and basically it's higher order logic, so you can even quantify over functions and work with them as you would do. An example of such a property that you could write in Isabelle would be, for example, the Goldbach conjecture, that for every even number greater than 2, there exists 2 primes y and z, such that x is the sum of the 2 primes, so every number of value at least 4 you can write as the sum of 2 primes. In order to write that well, you of course have to define first what is even, you have to define a notion of primality, but then you can try and start to prove such a property. What's the benefit of doing that in Isabelle? Well, first of all, it's a lot of more work than writing that just on paper or sketching a proof on paper. Because Isabelle is pretty nitpicking about every tiny detail that she wants to have explained. But in return, you get a high confidence that the proof that you have written is indeed a mathematical correct proof. Because Isabelle checks every reasoning step that you do. And the way this is done is basically, Isabelle is also implemented in a functional language called standard ML, and there the type of theorems, so the type of, there's an abstract type of valid statements that you want to be able to construct, and that's phrased as basically a module where you don't export the constructor of the whole thing, but you only export certain ways to manipulate theorems, and these functions that are exported are those that implement the proof rules of the higher order logic calculus. And that means basically, yeah, anything that you can prove as a theorem in the end has been derived by applying the rules of the logic that you're working in, and given that we have a consistency proof for the logic, that means the statement is true. Very, very simple. In a mathematical sense, saying it follows from the few axioms, like 12 axioms that we have in HOL, just by using the deduction rules that we have. So basically the ML functional type system ensures that all the proofs are correct. And that's the kernel. That's a tiny part of Isabelle, a few thousand lines of ML code. If you scrutinize that and be sure this is the way you want to do it, then you're good. But it would be pretty tedious to actually code everything in ML. And therefore there's a huge user interface around that build, which help in searching for proofs. So rather than precisely saying, now replace, unfold this definition of this function in this thing, or yeah, the thing is, I don't want to look into the project.
Yeah, this is okay.
This is okay. Okay.
Sorry for that. Before you were just half of it and it looked really fancy.
Right, so there's the implementations for tools that help you search the proofs, where you just say, okay, I want to prove that by, say, term rewriting, similar to what GHC rules does, or I want to use some Tableau prover there. So that's a large part of the ecosystem of Isabelle. And the other thing is, of course, supporting to define functions, because higher order logic in itself is not a programming language, it's just logic. And basically the whole programming stuff that you will see tonight is just built on top of that with thousands of lines of ML code that basically construct a programming language into higher order logic. Right, so that much the theory, let's get started. Everything that you see at the moment is the graphical user front-end called Isabelle JEdit, because it's built on the JEdit prover. And I thought, well, every functional programmer starts programming with lists, right? So this is the most basic thing, so let's see how we can do that in Isabelle. So, and this is not, I mean, of course there is an Isabelle library of lists with a richly developed API and theorems about it, but it's no use showing you that to understand the thing. So I thought, okay, let's define a type of list, a data type of lists. So there's a keyword data type similar to data in Isabelle. Type variables in Isabelle are written with one of those apostrophes at the beginning, and then the type constructor is actually written postfix to its arguments. So the other way around as in Haskell. And let's ignore that part on the right hand side. So the list is either nil or it's a cons of an element of the list to the rest of the list, just as you would do in Haskell. And then you can define nice syntax for that if you want to. So you can define syntax like, okay, I don't want to write list here, but I want to say, okay, the list type is just written like with square brackets as in Haskell. The empty list is just written with 2 empty square brackets. And cons will be written as the infix constructor with a colon. And the numbers here are just precedences used for parsing and pretty print. So this is really, really nice. And of course, in Haskell you have the ability to write long lists in this syntax that you write X and the rest of the list. So let's instruct the parser to do that. And that gives us a data type of lists, a data type of finite lists. So what can we do? Let's define a function. How about appending to lists? So fun, this is another package, helps with defining things. So we want to define a function append. The 2 colons then becomes the type. So come on. Hey. It takes 2 lists and produces a list. And how do we define it? Well, appending the empty list. And of course we can also put in some nice syntax, say, and write append as an infix operator plus plus, as you know from Haskell. So appending the empty list to something is what? Something, right? And then of course we have that this is supposed to be x cons x is plus plus y squared. A very, very simple recursive definition. So what can we do with it? Well, the first thing we functional programmer normally do is write the test program and see whether it does what it should do. And that's actually something you can do in Isabelle. You can say, okay, let's use the Glasgow Haskell compiler to evaluate the definition that we have. Say 1, 2, 3, append it to 4, 5, 6, and let's say these are integers. And then here is an output panel, and we see that's what we get. So you can actually run the programs that you write here. What happens in the background is that this function definition here is compiled into Haskell. The whole thing is then compiled using GHC to machine code, executed on the machine. It will print that list as an output. That is reparsed and then displayed here. And you can actually look at the code to which the append function is compiled by just saying something like that. And that creates a file module demo, which does some prelude imports, but the important thing is basically what you see here. The data type from up here is translated into a Haskell data type, and the function that is given here, these two equations are translated into the append function. That's basically what happens.
Quick question about the syntax. So you're using those double quotes in a bunch of places. And
Right.
It's makes an impression like you have 2 layers of syntax.
Right. There are 2 layers of syntax. There's there's the outer layer where basically all the commands live, like fun, translation, data type, section, and stuff. And then there's the language of formulas and types, and they have to be enclosed in double quotes or in those fancy brackets that you see here in the sectioning title. Right, so there are 2 layers of syntax, and basically just by all these syntax declarations that you see here, they only affect the inner syntax. The outer syntax is harder to manipulate, and yeah, it's basically the command that tell Isabelle what to do. As a first, I mean, yeah.
Could you also show the code translated to Scala?
Sure. That's the Scala version.
Yes, one language to program them all.
So you can also do it in OCaml. There's the OCaml version, and standard ML is also supported. And you could even write your own backend for another language if you wanted to. So right, yeah, it's pretty flexible, but let's stay with Haskell because that's what we're familiar with. Further questions? Okay. Peter.
So I have a small question. Maybe it's a little irrelevant. So in the top line of the module, you're exporting lists and append.
Right.
Haskell's a little bit rusty, but that says you're not exporting the constructors of lists.
Right.
So you can't actually use append on any interesting data.
Indeed. So if I want to use also the constructor, I would have to specify it.
Okay, and then that goes as well. Right.
Yeah.
But now it's exported the other constructor too.
Yeah, because it always either exports everything. So, but yeah.
Okay, cool.
Yeah. If there's one constructor, every constructor is exported. If you want to work around that, you would say you define a new constructor const, and you just say you export that thing. Then yeah, as you basically know. Okay. First property I would suggest to prove as well. Actually, so properties we want to prove are typically called lemma or theorem or proposition or corollary. Lemma is the most frequent name. So what happens if we try to append the empty list to the other side? What do we get with this definition? What would you expect? Well, exists, right. So, and how would you prove it? Induction, right. So let's write a proof and do induction on axis. Right, that gives that. So when I write lemma, now I have down here in the output basically the proof state, which tells me what I have to prove. And if I say, okay, I want to do induction on that, then I have to prove two cases. One case nil for the empty list constructor, and one case for the const constructor that we have. And in each case we have to show a case. So for nil, of course, axis is replaced with nil. And we have to prove that. Well, how do we prove that? Well, if we look, this is actually an instance of the equations that we use to specify append. Namely, the first one, if we put for y is the empty list here, then we get exactly the goal that we have here. So let's give that a name. And say, okay, this follows by the fact that append nil. And then we get something, okay, we show this, and it's been successful to do that, and when we go to next, one of the two goals, one of the two proof obligations for the nil case or for the const case has disappeared. In the const case, what we have to prove is, well, we may assume the induction hypothesis for a list, and we have to prove that the property also holds if we prepend an arbitrary element x to the front of the list. So how do we prove that? Well, the problem is that there's very little space here, so let's move that here, so that we can see the function definition up here. Oops. So we had append nil, here we have append applied to some cons. Well, we could think about using this equation, right? So let's call it append cons. So we have, right, we wanted to prove that this whole thing holds. So the case is just an abbreviation for this thing. So let's do it in several steps. So first let's say x cons x is prepended to that thing is, by the equation up here, x cons x is prepended to the empty list, right? And we know how to justify that because this is an instance of that thing up here. And then we want to say that this thing here now obviously is the right hand side. And let's for a moment just say sorry. Sorry just says, okay, accept this statement without a proof. And ultimately, once you're done, you shouldn't have any sorries in there. And because we're doing here several equational steps, Isabelle can chain them together, and we then have, okay, this left-hand side is basically the same as that. That's what we have to show. So that's what we have shown. So this is done. So what you see here, the bias is basically a one-step proof that is automatically discharged, and what's behind is basically the justification for why this proof step should hold. And this is just refers to what we have proven in the previous two steps. So how do we prove that? Well, you see in the cons case, we get as an induction hypothesis that this actually holds. Right? So we could say we have that, and if you parse that, well, we have this equality, and equality, well, if we substitute equal things with equal things, that should hold in any context. That's what we want to do. And this kind of substitution can be done by simplification. We just have to say, okay, just use the assumption to do the rewriting. And now Isabelle has accepted the proof and then said, okay, we have this theorem that this holds. We can also give a name. like append nil2 to the whole thing, such that we can later refer to it. That's the first induction proof that you would do. Now this is pretty slow for a very, very simple property. Question so far?
Could you not print it to something like latex?
Yeah, you can actually. So what do you want to pretty print? This
Like
stuff that I've written? Yeah, Isabelle also has a backend for printing this kind of stuff to LaTeX. Indeed. It's just a bit of more work to set it up, but it's yeah. I mean, you've noticed that I'm using a bit of more syntax than the normal ASCII alphabet provides. So Isabelle has a large range of fancy notation that you can install to make things look as mathematical as possible. Far more than you would expect in other theorem having other theorem proofs. Right. Yep.
One question. So, usually those kind of systems, like Isabelle, have some additional, tactics or whatever that can
Right.
automate some of those kind of.
Right. I was getting
those
towards
simple,
that.
Proof could have been probably, proven out magic, right?
Yeah. Right. So let's try to do that actually. So now we had. Oops. How do I? Yeah. Let's place that for a moment to see. So what we have done is basically two equational steps. And we could also have done that in just one step. Right? Because what SIMP does, this is one of the proof search engines that are there, one of the tactics. And what SIMP does is basically, it has a set of rules, and we can actually inspect what it does. It just does term rewriting, but right. So let's trace that. Let's look at the simplifier trace, and that's here. We've invoked the simplifier. The simplifier is term rewriting engine, and what it does is, well, first of all, the defining equations from functions are used as default rewrite rules. So, like. When you execute them, he will also try to rewrite. So that was what we did in the first step with by fact, right? And therefore it replaced the one by that. And then it says, okay, yeah, now we have the induction hypothesis flying around in our proof context. It's actually given to the goal state. So it's using that, trying to rewrite that. And now we have rewritten the left-hand side twice, and now we have to do that. Well, it knows that this is true, so this is another thing of term rewriting, so it reduced everything to true, and that's trebly discharge. So yeah, there is this way of doing things, but of course you want to do that, and of course you can do the whole thing much shorter by also, I mean, the nil case is also just an instance of that kind of rewriting. So now we're down to a one-line proof.
And then you print that away, right?
Yeah, you can also print that to LaTeX. But so you have a very, very wide range of level of automation you can achieve, you want to achieve. But what you always have to tell it explicitly is, I want to do induction or these kind of things. That's nothing it would figure out by itself. Not like other systems that have induction heuristics. There's nothing like that. More questions?
In which case do you prefer these manual steps?
So, I mean, it depends on what I want to achieve. So for a really, well, if I want to precisely present, okay, this is the proof and I want humans to read it, I would go more into details. If this is just a technical lemma that nobody cares about and everyone expects it to be true, and the goal is let's get the proof through, you of course want to use as much automation as possible. Sometimes it's just not possible that automation finds the whole thing. So I mean, the simplifier is a bit more powerful than the GHC rules engine, but it's not magic, right? So if you can't prove it with rewriting, then, well, either use something different or give him some hints like, okay, there's an intermediate statement, and it's somewhat an art to find a good balance between readability, maintainability, and effort of writing it. And it really has to be done on a case-by-case basis.
How is the performance like in terms of scalability? If you have a lot of potential rewrites that you could apply at every step.
Right, so the simplifier doesn't backtrack, basically. So if you have, and with such a function definitions, of course, I mean, there's the rewriting system that arises is confluent and terminating, and then you know, okay, by just simplifying both sides, they will end up at the same thing if they're equal. And this is pretty fast because you don't backtrack, you just basically execute symbolically the whole system, the function. So I've hardly run into scalability problems there. As soon as you start with conditional rewriting, which is also something that the simplifier supports, so you can write an equation and put some precondition to it. If you're not careful as a user, you can quickly get exponential runtimes of the simplifier. But then, yeah, you want to be more selective, and what's also commonly done is that, yeah, you not just call symbol, but you also tell him, oh yeah, and use additionally this bunch of rules, for which you of course have to know the API a bit.
The other thing is implementation-wise, the simplifier converts the set of rules into a trie, so she can always dispatch in one symbol. So the size of the set really doesn't matter.
No, it's...
What I don't know, Peter, you probably know more about the SEL4 scaling problems. But just if you have that many lemmas, that storing them all in memory.
That was never a problem.
Was never a problem. I just heard that you had like 16 or 32 gigabyte machines.
Yeah, but that was, I think, mostly for manipulating the terms that back the definitions. They got massive.
Yeah.
Okay?
No.
Not the lemmas. The lemmas are always kind of small, but the terms that back them can get huge.
Okay.
So these tries you're talking about, these proof nets, they never were a problem.
Yeah. Right. So there are a few cases like records where people have implemented on-the-fly proof rule generation. So where you don't have to store all the theorems in the proof net, but you just look at the goal and on the spot you create it. And in SEL4 that was one of the cases to make the thing fly, because they had like a record with 500 fields or so. If you want to prove, okay, how each accessor function interacts with each update function of a record field, you get 500 squared many combinations, which would just be too much. So that's where you then do some more clever engineering. But for normal use, it's completely simple. Right. So that was the first thing. Next function. Let's do list reversal. How would you do it? Who wants to have a go? Okay, I do the easy case.
You want it to be efficient?
Not really now. We'll get to efficiency later. No, so the easiest thing is just reverse the whole thing and then append it to the end. So that's also a rule of thumb. Normally you want to be your definitions as simple as possible, such that the proofs become simple. And efficiency is a later concern. So as you can already see in this lemma, higher order logic doesn't have a notion of efficiency. Because otherwise, appending something to the end of the list, which has linear runtime, couldn't be equal to the list which has no runtime at all, which is constant time, right? So there's no notion of computation involved here, and accordingly efficiency is not a matter. Right, so this is the simplest thing, and for the rest of, oh right, we can of course export the whole thing, and here you now see, okay, even though I just export reverse, it has figured out that reverse is implemented in terms of append and also included append in the definition of the thing that we wanted. Right, so once you've defined a function, you've convinced yourself that it does the stuff it's supposed to do. What you do is typically start to prove a few lemmas to prove how they interact. So for example, what would be the interaction of reverse and append. So if we reverse the append of two lists, we probably just want to reverse the first list and then reverse the second list, right? No, it's not right. True. Actually, Isabelle tells us that. So there is a quick check function in Isabelle that whenever you type a theorem, it's being run. It tries to compile it to code and do some randomized or exhaustive small-scale testing. There are various generators, and here it says, okay, yeah, for these two lists, actually we get something different, and then it's up to you to figure out how to do it. Of course, you know the right result. And how do we prove it? Well, we have recursively defined functions, so we want to do that. How do we do that? Well, let's try rewriting again. Doesn't work. It says, okay, there's something remaining here. What could that be? Well, if we could use that, this would be simple. So we can tell him to additionally use, in addition to the rules that are there by default, namely the definition theorems, we also need additional properties, and we can have them there and explicitly add them. Or we could just say globally it's always a good idea to use this rule and declare it globally as something to be used by the simplifier, and then we don't need it down here anymore. In that case, it's shown trivially. Let's see what we can do here. Damn it. Why doesn't this work? So let's make this a bit bigger. So what we have here, okay, it has the induction hypothesis available. We have to do one proof here, but it says, oh, these two things are not equal. What do you do then? Well, should they be equal? Simon's nodding.
If the append is associative, it is.
Right, okay. So by looking at that, we see, okay, yeah, here there are these parentheses associating these two terms to the left, and down here, because we've defined append to be associative to the right, like it is in Haskell, basically the parenthesis is here and here, so we need associativity of append. And so let's do that. Access plus y plus z, right? Okay. Who wants to have a go at proving this? So, right. So this is a really simple lemma here. In that case, provided you have figured out the right induction variable, right? I'm doing induction over this thing, and I'm not doing induction over this variable. If I did that, the inductive case wouldn't go through. The reason why I use that is, well, append is defined recursively over the first argument. So the proof has to do induction over the first argument. And yeah, that's basically why it works. Why does this down here not work? Well, obviously we haven't told Isabelle to actually use the fact, and then so reverse of can works. And yeah, one can continue with that and say, okay, what is the reverse of a reverse? Well, this is of course axis. So we don't always have to write this nice style of proofs where you can LaTeX and pretty print nice proofs as we did before, but there's also a more interactive scripting approach which starts with apply, and then you directly operate on the goal state, and then you can say, okay, I want to go on the first sub goal, and how do we solve it? Well, we solve it by sim. Yeah, this works, and then we have another sub goal for x and axis for those two variables. That's what we have to prove. Let's see what comes out of here. Okay, and here we see, we have a reverse applied to an append. Oh, lucky us. We've just proven a lemma about that. And so this is also done, and then the proof is done, and that's the more interactive way of writing things. And then once you've written that, you can of course shorten it again into something very, very short. Right, but as you notice, reverse is not really the most efficient implementation. So now I'd like a fast implementation of reverse. Who can offer one?
Accumulator.
Okay, let's call it quick ref. Which type?
So we need, this to this to this.
Okay.
And then the first one, A, and then
Okay.
if the second one is empty, then it's just A.
Okay.
And if the second one is const, then we put the X over.
Everyone familiar with that kind of adding an accumulator? Okay, so that is proven. Now of course we want to have some thing. We want to say, okay, ref is the same as qref of the empty list and of course the list axis. So let's print that. Okay. Sim, first goal goes away. Second goal doesn't go away. Done. Done it. What do we do now? Well, we have an accumulator here, and we have a recursion that changes the accumulator. So obviously the statement we want to prove must also be general enough such that it works for arbitrary accumulators. So how do we generalize this lemma? Well, okay, let's start with qref a axis. So this is reverse of axis. And what do we do? So in case a is nil, this property holds. In case a is not nil, we get a counterexample, yes. But how is the behavior in overall? Well, it's the same as adding a to the end of the reverse text. But that's actually the property that qref characterizes. And let's try to prove that. Yeah. Well, if we look at that thing over here, we see again, okay, we have qref of x is cons A, but our induction hypothesis just talks about A. So maybe we want to prove that for all A, this property holds, not just for fixed A, which is then later generalized. So this still holds. Oh, looks better. Now there's no qref anymore, so the induction hypothesis has been applied. And well, we again see here something like associativity. And we're done. Hooray. Okay, this is then qref primed. And, well, we could of course now add that and we're done, right? Hooray. We proved that we can express ref in terms of qref. And what does that tell
Don't
us?
need induction, do we?
Good point. We don't, if we now look at what the simplifier really does is, we would notice that the induction hypothesis is never used. Because I mean, if we simply just drop that, the proof goes through as well. Good point. So because this is just a special case of the thing up here. But what I was trying to get is, we can say, okay, now please, dear compiler, implement ref using this equation, rather than the definition that we had initially given. And if we now look at this, we will see that we get the usual definition that we want to have. So we get basically the best of both worlds. Being able to write a simple definition up here, doing the proofs about the simple definition, then we can define an efficient version, prove them equivalent, and for compilation and execution we get a good thing. Right. So, questions so far? Any wishes, suggestions how we shall proceed?
Goldbach.
Goldbach. Yeah, sorry for that. I don't have a proof of that in my pocket. I have. Sorry.
From what?
Sure. Yeah.
I mean, there is a proof, supposedly.
It is supposed to be approved. Yeah.
The one from
How long do you have time to listen? Okay. Let's do something simpler. Right. So far everything looked nice and shiny. So let's define a function merge that does this. Basically it takes two lists and interleaves them basically in some sense of merge. So we have merge, of course it takes two lists and produces one of this kind. And well, merge, if we have the first list empty, then let's just take the rest, let's not drop anything. And well, it's certainly X, and now we could do a pattern match on Y's, but actually it's enough to swap the two arguments, right? You're not convinced? Are you? Well, actually, this is right, but you already see there's a red exclamation mark here, and there's a big error message here coming and saying could not find lexicographic termination order. So what actually happened with the previous definitions in the background was that Isabelle constructed a termination proof in order to make sure that you don't get an inconsistent logic by adding this function definition to the whole thing. That's what that's something that I meant to when I referred to, well, there are lots of packages that help with defining things, because higher order logic doesn't have primitive notion of recursion, that must be emulated or justified in some case. And the fun package basically implements the approach of well-founded recursion, so where the recursion has to terminate. And here we see, okay, yeah, it constructs a certain call graph. It has a size notion, which is the length of the list in this case, and it's trying different measures. So functions that should decrease whenever a recursive call comes, and because we have here some kind of permutation, so the first argument on which we do recursion suddenly becomes the second argument, and then there's one recursive call where the other list is being swapped in. We have a problem here. So there's a long version of the whole thing, where we first have to prove that we're covering all cases, and the cases are not overlapping. Because in theory there's also some support for overlapping cases, provided that the right-hand sides evaluate to the same thing. And then we have to prove termination, and for that we have to give a relation, so a termination relation, which in our case, well, we have a measure function which has to take two lists and produce a natural number that decreases upon each recursive call. Well, we're peeling off one of the elements of the two lists in each recursion, so let's just take the sum of the sizes, right?
So interesting. These lists, I mean, where is size defined?
Oh, size is defined by the Datatype package up here. I see. Right? So there's a lot of stuff going on behind the scenes where you actually they also define like selectors that you would do for head and tail, or let's call them like in Haskell, right? No, not 2L. You also get a map.
Head is usually partial in Haskell. How does it handle it here?
Oh, I mean, if you call. If you look at what it does, it's also partial. There's no case for the empty case. You will get a pattern match error.
Why is that no problem for the logic?
For the logic, well, head is basically underspecified. And, well, you just know that it will return something of the right type. The logic just assumes that if a function has a certain type, no matter what you apply it to, you will get something back. You just don't know of which element that is. And because in Isabelle, every type contains a value, so there's nothing like a void, there's always something that you could pick in the logic there. But yeah, this is one of the finer points of things. But yeah, you could do that. You can get a map function. You can also get basically a set function up here that converts lists into sets.
A fold?
No, oh yeah, I mean you get a recursor anyway. Right, so this is the primitive recursive function, which is a generalized fold, a more general, something equally expressed. Sorry?
Can you show its definition?
I can show you the equations. List.sims is probably.
It was there in a minute.
Yeah. List.rec is the better name for it. So, right, so for demo, okay, let's just use short names. So it takes basically the same as fold, nil case, cons case. Empty list is just a nil case. In a cons, the only difference to the canonical fold is that you also pass the tail of the list to the folding operator that you have. but they're equally expressive, so you can express the one in terms of the other.
What are the question marks?
The question marks, so, yeah. So,
There's some magic for everything, like literally everything. Just add something and it disappears.
okay, so Isabelle always has to distinguish between variables which are fixed and variables which you're allowed to instantiate. Right? So normally we don't write those question marks because here we say, okay, for all y's, nil appended to y's is y's. And if we want to prove, or let's put it down here. So let's go down here with the QRef thing. In the QRef thing, I used this universal quantifier to say, okay, I want to pull this universal quantifier through the induction, and here I had the universal quantifier as part of the inductive hypothesis, and I had to, well, I also had to do the proof for all A down here. Without the universal quantifier, basically the A could have been in the context, so I could have written something like A equals the empty list, and if there's no universal quantifier, I would be able to unfold this assumption here and replace A with the empty list, because it's not quantified again. Well, that's why we have to distinguish between fixed variables and variables that we can instantiate. And so with the universal quantifier here, QRef, right. With the universal quantifier, I'm explicitly saying, okay, this is quantified. And in Isabelle, by default, if you write a lemma, all the variables that you don't quantify will eventually get quantified. And once the proof is over, they will be generalized to something that you can later instantiate when you use the theorem. And so that's why instantiatable variables are marked with a question mark. And right, so if you want the usable form of the theorem, you have all the question marks over here. And if you say no vars, you make them fixed, just throw away the question mark, and it's just used for preprint. So yeah, there is something almost for everything, but right, so that's what you get here. You get a lot of other theorems from the Datatype package, proven and stuff. Yeah.
Could we get back to the question from Simon about this head and partiality in Haskell and what happens in Isabelle? I didn't quite get that.
Okay, so in Isabelle, the underlying logic assumes that the function is always returns something of the correct type.
Okay.
And right, so damn it, you don't see it.
Can you do the switch to ML and then do a print theorem?
It will be the same again. I mean, I don't want to print Isabelle term syntax here.
All right.
Yeah, no, there's no way to.
Well, you could write the definition with arbitrary.
Yeah, it's okay. Anyway, head of this is basically defined as case x's of the empty list, then this is undefined, or x cons something, then this is x.
So what does it mean, undefined?
Yeah, we'll get there in a moment. Just that you. So you see the proof is accepted. This is really the definition. Undefined means in Isabelle, well, it's axiomatized to be a polymorphic value of any type.
So it is like kind of Haskell.
but you don't know what it is. Right? So, and you don't know anything about it, whatever it does, but it's just used in those cases when there's...
It particularly means you can't prove anything about it.
Right.
The only property you have is that undefined is equal to undefined, because
Exactly.
sort of consistently, the element is consistently picked.
Yeah. So you have one fixed element, which can be sometimes an unrealistic assumption depending on how you define things, but normally it's pretty fine and doable.
Does the code generator have a notion of partiality? So could you tell it, please make sure that I don't generate partial functions?
No. So there is, well, what is partiality in that sense? I mean, it doesn't.
So I guarantee that it always returns, so that for
Right.
the Haskell program always terminates with a result of the right type.
No, you can't do that. You can't do it easily. The reason being precisely this possibility to exchange equations arbitrarily. So I could also write an equation like ref x's equals ref x's. Quite simple. And then do stupid as the code equation and guess what the code will be. Right, and so it's not doing a termination proof upon code generation anymore, so it's inherently partial. Yeah, let's do the Recursive code again and do that. Okay, back to termination maybe. So we had this and we said, okay, maybe we terminate if we, or in order to prove termination, we could just sum up the sizes of these two functions. We have to prove that the measure yields a well-founded thing, but this is, let's do it in apply style simp, and we have to prove that the recursive call actually decreases in the measure. So the original call is, we have x comes x and y is in the first argument, and the recursive call is that part, and we have to prove that this is decreasing in that relation. That's also automatic, and we're done. And, well, like there's something for everything, Isabelle can also find that automatically, but it's not a lexicographic combination of size functions, so size change is just some more powerful termination prover, but it's not called by default because it may take very, very long time, and so users are asked to explicitly write when that is needed. Okay, so now we have proven that merge terminates. We can do the usual reasoning that we want to. For example, say, what is the size of the merge of two lists? So the length of the two lists, well, it's of course size x's plus size y's. Right, how do we prove it? Who's for induction? Nobody, but of course, on x's or on y's?
Both variables.
Both variables. Why both variables?
I don't know. Do
Right.
we swap them?
Yeah, we swapped them. There's, you're right, but you're spoiling the whole fun. So,
I'm sorry.
so the empty case is again very simple. But if we try the cons case, we see, okay, we get the induction hypothesis for size of merge of x's and y's. But actually, we would want to have it as size of merge of y's and x's, right? But because we're doing induction on just the first argument, well, we're not allowed to just plug in something else. And why doesn't it work? Well, the previous functions could all be basically proven by terminating by just looking at this argument, the second argument here in QREF decreasing, and that was what we did induction over. Down here we had a more complicated termination proof, so we need a more complicated induction rule. Fortunately, the function package, once you've completed the termination proof, basically gives you the induction principle that you need to prove properties about this function, because it precisely captures the recursive pattern of the function. So in order to establish any property P on two lists A0 and A1, it suffices to establish the property on the empty list and any other list. Y is up here. And in the inductive case, well, we have the induction assumption for the recursive call, P of Y's and X's. And we have to prove that the property then is also holding on the original arguments of the recursive, that cause the recursive call, namely that. And so we want to do it on both. And the whole thing works again. Nicely. So that was termination proofs. And if you don't mind, I would then go to the last topic that I've prepared, infinite data. So as you might think about, well, everything should terminate. How can we work with infinite data and stuff like that? And by the way, our lists are anyway finite because they're a data type. So it's just finite lists, and that's the reason why we can prove anything with induction on that, right? If it was something else. If we had infinite elements in there, we wouldn't be able to reach them in finitely many steps by adding elements to the empty list. And therefore, they wouldn't be covered by the two cases that we're doing. And, well, there are different definition principles. Oh, nice, yeah. Yeah, I could have evaluated merge and do the size proof. I had an idea about proving how merge and append relate, but let's go to streams. So a stream is basically nothing else but a list where we don't have a null constructor. So we just have an s-cons. You've seen the selectors, stream head and stream tail. We're writing now hash for the stream constructor, and the main difference is basically this part here at the front, saying it's a co-data type. So rather than the smallest type that would fit with these constructors, this is the largest type. So, and accordingly, we can use different things. For example, we can define the list of ascending numbers, or the stream of ascending numbers, called up. And up, well, starting at n, well, outputs n. And the rest of the list will be up of n plus 1. You notice this is not fun here, this is called prem_correc, because this is primitive co-recursion, and it does a bunch of other checks than fun, whereas fun tries to prove termination. Here we try to prove productivity. So it proves that actually before you do a recursive call, you do produce a constructor. So you can evaluate the stream to arbitrary depths by finitely many recursive calls. And that of course gives us a bunch of theorems. So the first two are the same, they're just a specification equation that we got. But there are also the simple rules where you get basically how the selectors do that. And they're basically like in code pattern matching, triggering then the evaluation of the thing. Because if we stick this equation as a rewrite rule into anything, well, it will work always. Once there's an up, well, let's unfold. Oh, there's an up, let's unfold. Oh, another up, unfold, unfold. That's a good way to run out of memory very quickly. Whereas if you just have the selectors lying down here, well then these selectors basically inspect the stream in some sense of observation, and well, they're gonna away, and so these are the simplification rules that are used by default. Yeah, I've defined a take function that converts streams into lists, well, a finite prefix of it, using natural numbers, which are by default represented in Peano as arithmetic. So you have 0 and n plus 1, and n plus 1 of course takes the head and the tail, and then I can also evaluate and work with streams by compiling them to Haskell, because Haskell is lazy. So yeah, streams are also just represented as data. The arith int is Isabelle's wrapper around Haskell integers, which you can see down here, so there's a bit more of code flying around here. But otherwise it's more or less the specification for up that you've seen. It's n up of add 1 to the int of integer of 1 of integer. There's some boilerplate flying around, but normally the Haskell compiler is pretty good at eliminating that. And that works. If we compile that to a strict language like Scala, yeah, we get a second flow. So, but with Haskell it works. And we just had the merge operation, right? For two streams. We can define that in the same way for co-data types. And now again, we don't have to prove termination, we have to prove productivity, but there's one constructor here on the outside which guards the recursive call basically, so we're fine. And yeah, we can also evaluate that. We can define a map function on streams. Actually, we don't have to. We could also just say have it generate up here, then I don't have to have it, but let's just make sure that we have this. What? Okay. Map. So. Okay. Yeah. So, in order to prove anything now about streams, we can't use induction anymore, because they're infinitely long. There's no base case. We wouldn't know how to start. Right? Instead, what you would do is to use co-induction. Yeah, let's move that again to the bottom. It's more readable there. So what co-induction gives us is, well, in order to prove that two streams are equal, we have to prove that their heads are equal, and we have to prove that their tails are equal. Topology. But actually we don't have to prove that their tails are equal. We can also prove that their tails satisfy the same property that we started with. So basically we have a bisimulation between the two streams if we consider them through the selector's head and tail. And then the co-data type property says, okay, then actually if I have a bisimulation between two streams, they're actually the same stream. And that's what we can do here. So if we map a function over merge, well, we can merge the transformed streams. And, well, now we use co-induction. We're saying, okay, we're using co-induction to prove equality of streams, and we want the function axis and, or the streams axis and y's, that they're the thing where this property varies. We want that to be arbitrary such that we can show, okay, we can pick other ones. And what we then have to prove that, just as I said, both streams, both sides of the equality have the same head. And the tails are again, the tails of each side are again of the form that we've specified. So there are other streams, x is a and y is a, such that the tail of the left-hand side has the formed as map of merge of those two streams. And for the same two, x is a and y is a, the merge of the left, the tail of the right-hand side has the format of the right-hand side again. And one of Isabelle's tactic proves that completely. So this is something you can't prove just by rewriting, because rewriting will not know what to do with these quantifiers. You need something more. You can be very explicit here. So we could say, okay, for those two streams, we could say, okay, use the tail of the original list as the witness to the first existential quantifier, and we could similarly say use the tail of the second stream for the second existential quantifier. Now we would have again plain equations. Well, we can just say sim and it doesn't work. Who knows the error?
What's what? Two x's?
No, we of course have to swap it, because merge keeps swapping its arguments. And it still doesn't work. What a pity.
Well, you could put.
Yeah, of course, it's why is this not being taken the tail of? Right, merge just peels off the tail of one argument and then swaps the two things. Right, and then we're done doing that proof, and then we're done. But yeah, these instantiations Otto is able to figure out by himself, which basically brings me to the part that I wanted to present. So if you have any questions or want to see something formalized which doesn't take as long as Fermat's last theorem.
I have a question.
Sure.
So in Haskell there's the streams data type, like the library, which optimizes, turns lists into basically co-recursive data types, but not expressed using recursion.
So you mean stream fusion, or what?
Yeah, stream fusion. That framework basically creates a process that acts like a code data type. So couldn't the Scala export do this, or is that too complicated?
So there is currently one person working on actually doing implementing a preprocessor to the code generator that can translate data types into lazy data types that are implemented lazily, basically using closures that are delayed in terms of evaluation. There's no optimization going on there at the moment. And there's another library which implements list fusion,